Am I experiencing friction right now?
Yes.
Why?
Do the carpet?
Say it again?
Do the carpet?
Just because I'm touching the carpet, does that mean there's friction?
No.
What's required for there to be friction? Say it again?
Gravitational pull.
Not necessary for friction.
Opposing force?
Opposing what?
Opposing you, like going in the opposite direction.
Say it again?
Going in the opposite direction of you. Like,
Yeah, but what would be the opposite direction of me right now?
I don't know.
Which is part of the issue of,
Yeah.
in order for there to be friction, it does have to oppose some relative motion. But assuming that I'm standing perfectly still, my legs were probably closer together, there's not necessarily any friction acting on me. In order to walk, I need friction, but there's not any friction acting, necessarily any friction acting on me right now. Probably if my legs are just spread a little bit, there is friction acting to keep my legs from spreading apart. Depends on how strong my leg muscles are. So it requires relative motion. Let's just take the simple case of one thing sliding against another. Got track. Was there relative motion between the track and the marker? There seems to be a consensus of 1. Anyone want to back Briley up? Some people might have done some subtle nods that I missed. Looks like no one's got your back there, Briley. Was that a head gesture one way or the other?
Doesn't guess.
Okay, were you nodding yes? Do you agree with Briley that there was friction acting on the marker? Okay. Getting mostly blank stares. Well, what are the criteria in order for what are the requirements for there to be friction?
Two moving opposite to each other.
Say it again?
Two objects moving opposite to each other.
Was the track moving opposite the marker?
Well, it was listed.
Yeah, that's my hesitation too. Yeah, well, maybe, depends on how you wanna look at it.
Parallel to surfaces of contact.
Okay, it is parallel, so there's contact, that's a requirement. It would be parallel to the surfaces of contact, I agree with that. Was there relative motion between the two? Again, you got one person saying yes. Okay, we got a very subtle nod there. Gail, okay, we got that side, the middle right now, underrepresented. I guess you're the spokesperson for the middle.
So yes.
Pardon?
Yes, because there's two objects with desired relative motion.
Yes. So there has to be desired relative motion in order, and there definitely was, not only desired motion, there was motion. That marker was moving down the track. Or, from a slightly different point of view, the marker stayed still and the track moved this way. We all moved this way while the marker stayed still. Generally not an easy way of looking at it, but
So when
legitimate
you're-
physics.
When you're standing, is there friction acting on you?
Maybe. It depends on how my legs are. Probably as I normally stand like this, there is friction acting, keeping my feet from my doing a split.
What about standing still?
Yeah, standing
Like,
still.
I mean,
If I had my feet together like this, probably not a lot of friction. Not that ice is frictionless, but I have stood on ice before without falling. And I have slipped and fallen. All right, so if there's this desire to move against one another, what is actually causing the friction? Okay, so why do two objects touching cause friction there? Have you ever dragged something over the ground?
Yes.
When is it harder to drag it over the ground?
When it's
Pardon?
just wet.
Okay, so that's a. We'll generalize that in a moment. What else makes it harder to drag it?
Obstacles.
Sorry?
Obstacles, like rocks, when it
Ah.
comes to rocks,
Alright.
bumps.
Anything else?
Are you talking about just the ground or
Let's generalize it. What else?
the
Not just the
weight
ground.
of what you're dragging?
It's gonna turn out it's not the weight, but it is related in this particular case. Let's see, where are my masses? Really need more thinking about. Guess I can take these two. There was a thing of hook masses in here. Does anyone see it? Well, we'll go with these. All right, these do not weigh the same thing. Surfaces feel relatively the same to me using my fingers. This is brass, this is aluminum, do not weigh the same thing. I think before Sasha verified they don't weigh the same thing. Do you agree that they still don't weigh the same thing, or are you skeptical? Would anyone like to verify that they do not weigh the same thing? They got your back. All right. So, if weight is an issue, this would have more friction than this does. So, if I put them on here, I guess the surfaces are not quite the same. The track wasn't the same. They both started sliding. Obviously, this slid more. Let's suppose I put them here. Probably just off camera. Which is going to experience more friction if I let go?
The brass.
Brass more friction? So if it's experiencing more friction, would you say it's going to accelerate less? More?
I guess.
One of those?
Yeah.
If it was experiencing more friction, it would accelerate less, wouldn't it?
Okay, because you have an additional force opposing the motion. So if I let go. So what was the difference between those two situations in that the track thing?
The surface.
They were on a surface the whole time.
Pardon?
They were on a surface the whole time. They were falling in the air. You dropped them.
We do it slightly differently. I'm going to take this piece of paper, going to pull it along the table. Is there friction acting on the paper? Right, there's contact, desired relative motion, yeah, there is friction. I put this piece of brass on it, and now I pull it. Is there more friction, less friction, or the same?
It's the same.
Same friction? So if it's the same friction, so I'm going to accelerate it like this. And then I put this on there. It takes the same amount of effort on my part to get them up to speed.
It would be more because it's slightly heavier.
What's heavier?
Not necessarily.
Paper. Because there's more weight pushing down on the paper.
Ah, but that's, actually there's, what weight is acting down on the paper?
The brass thing.
What force is the brass thing exerting on the paper?
It's not moving against the paper. It's moving with
Is
it.
it normal force?
It is. It's a normal force. The paper It is more difficult, and you can come up and experience this for yourself. It does take more effort to get that moving than it does to get that moving. Despite what some of you said. The weight is between the object and the ground and the earth. The paper weighs the exact same as it does whether this is on it or not. The paper is the same. But it is harder. It is not the weight that is causing the friction. It's the normal force. Normal force is basically, I got two objects pushing against each other, and the normal force is keeping, in this case, one hand from going through the other. The greater the normal force, that means the greater that these two objects are being pressed together, the more normal force there needs to be to keep one from going through the other. So, if I think about it, sort of interlocking pieces like this, the more normal force, the more that these pieces are jammed together, and the harder it is to get it to move lateral. It's much easier to move it like that than like that.
So if the normal force is greater, what happens to the friction?
It goes up.
It goes up.
More normal force, the more friction. There is a direct link between the amount of friction and the amount of normal force. But cross that one out without normal force. And these two things sort of get combined into one thing. The surfaces. So it turns out, really, in essence, the two things that really matter are how tightly are these two things pressed together, in other words, normal force, and what are the surfaces like. And that is surfaces plural. So if I'm trying to figure out the friction involved between the track and the brass, it is between, this is probably aluminum and brass. It is not between, it's not just what this surface is like, it's the combination of surfaces. So we got two things going on here when you're dealing with surfaces. If I have an object on a ramp, if we zoom in, it is not perfectly smooth. As you try to move the two surfaces, how interlocked are they? This is one of the things that's going on. So the rougher the surface, the greater the friction. The other thing that's going on is if they're pressed tightly together, that means that these atoms are close to these atoms, and there's a natural attraction there also. So we've got this, at the microscopic level, this, I guess these tiny little normal forces as one thing tries to move against the other, as well as there's an attraction there. Either one is trying to keep them from moving. And so there are two theories. Theory number one. Friction is going to build and build and build and build until it hits a breaking point, at which point it will start to move. The object will start to move. So if this is friction versus applied force. So as I push against this table, there's a little bit of friction opposing the motion. I push more friction. The friction's matching me until I get to a breaking point which it starts to move. This region in here is known as static friction. And this right here is known as kinetic friction. Static, not moving, kinetic, moving. Theory number, oh, yes, Elizabeth.
So if the friction is moving, why would the line stay still?
But why is this constant?
Yeah.
Because once you get it moving it's not really jammed together anymore, it's just slightly off the, as long as the surfaces stay the same and the normal forces stay the same, there's no reason why it would change.
So it wouldn't be like all over the place if it was moving.
If you wanted it, ideally, no. In reality, surfaces are not gonna be constant the entire way, there's gonna be small little fluctuations, and so you would get these small little variations, but as far as we're concerned, constant. And we'll eventually get into why I'm not more specific than that. Theory number 2 says, once you get it moving, it's easier to keep moving, and that's because the friction drops. So theory number 2 says, yeah, the static friction builds and builds and builds, then it'll hit a breaking point, at which point the friction drops and it's much easier to move. Again, this is the static. And this is the kinetic. There's a very clear difference between these two graphs. And yet, there's nothing definitive. I tried to find somebody who actually has done experiments. I found a college senior who did a senior topic on this. It's still, there are really large error bars when trying to figure this out, and it wasn't particularly definitive. But I couldn't find any academic journal which addressed this. All right, so in both cases, kinetic friction, it is a constant. And so in this model right here, we would write it as kinetic friction is equal to this number right here. This is a mu. It's a Greek letter. It's like a U with a stem in front. So it's a U with a stem in front times the normal force. And so this number right here, this is the coefficient of kinetic friction. This region where it's static, you reach a breaking point. This is sort of that maximum static right here, Fs max. And that's maximum static is equal to the static coefficient of static friction, or the static coefficient of friction. Probably coefficient of static friction is more accurate, times the normal force. Now, typically, the formula for static friction, because the static friction will build and build and build till it hits that breaking point, it is often written as just, if I drop the max, static friction is less than or equal to mu Sy. And that's just saying that there's a breaking point. Once I get past the breaking point, I'm now dealing with sliding going on, it's static. Over here, formula is slightly different because it doesn't drop down. What these people claim is that whenever you're trying to find this coefficient here, there are so many errors involved, you get huge error bars, it's really impossible to differentiate between the two. And so they would just write friction is less than or equal to Uy. And that's the coefficient of friction, and it's just a single number. Now, why has this not been resolved? Because this formula right here was figured out in the late 1700s. Got a couple hundred years, and no one's actually come up with it definitively. Well, friction is an engineering problem, not a physics problem. Engineers, very practical people, they have something that works, why bother going any deeper? Physicists don't deal with it a whole lot, so they leave it to the engineers to figure it out. and the engineers, as I just said, have something that works. There are some groups, I know there's a group at NC State that is trying to get something deeper than this, but I haven't seen a whole lot other than just, that's as far as I've seen, basically, the two graphs. Questions up to here? Later on today, we're going to assume this model, that these two numbers are different. So how do we do that? Let's do something with numbers. I'm going to have a block here, not the carts, but I'll have a block, I'll have a table, I'll have a pulley. I guess the table will really go like that. Spring, and I'll have something hanging down here. So this is hanging, and this is, I think I call it a block. WBH. Yeah, I forget what it stands for. So this is hanging, that's the one that's gonna slide. I know that the amount of friction here, I know that there's friction acting on it. I got tension acting this way, I got weight acting down, I got normal force acting up, I got friction acting back. Let's assume static for right now. The driving force here is gonna be whatever the weight of this is. That's what's gonna move the whole thing. This friction is trying to stop it. So as long as the driving force here, because again, I got weight acting down, I got tension acting up, that's just equal to the mass, hanging mass times G. So that's my driving force. This is my opposing force, and as long as those are equal, it's not, if it starts at rest, it's gonna stay at rest. The only way I can get it to move is if that is bigger than that. So I put some, so let's figure out what that's gonna be. My static friction, I'm looking for that breaking point, so we're looking at a maximum static friction. That's gonna be equal